Understanding physics. This video is about the assessed practical number 1, which is standing waves on a string, which is a transverse standing waves. Now, this is the equipment that you'll be using. You'll certainly be using a signal generator. What does a signal generator do? It generates a signal. It generates a sinusoidal AC signal. If you're using this one, make sure this knob here is on the sine wave, so you're getting sinusoidal AC, and you can change the frequency. This knob here changes the frequency. You can change the amplitude if you need to. Okay, this machine does other things as well. It can give you different waveforms. You can actually use it as an amplifier as well. But we're just using it as a signal generator to generate a nice sine wave, and it has a digital display of the frequency on the front, this particular one. A vibration generator, and you connect that to the signal generator and it vibrates at the same frequency. You use now, don't worry about impedance. Basically it's the same as resistance really for AC. You use the 4 ohm output. So the green one is the common one, and then the 4 ohm output, and that goes to the vibration generator. The high impedance output goes to an oscilloscope, because an oscilloscope has a high impedance, but for a low impedance goes to a vibration generator or a loudspeaker. You need a bench pulley. I suppose you need a bench as well to stick it on. You need some string, you need a meter ruler, and some 100-gram masses. Okay, you might use 10-gram masses as well. I don't know, I never bother. I usually get away with just 100-gram masses. And you set it up like this. So you've got your vibration generator connected to the output of the signal generator, and you've got your string there. You're putting your string in tension using the masses, and what you do is you increase the frequency slowly from 0, and what you will observe, what you should observe, are standing wave patterns. You should observe standing waves occur at particular frequencies. Now, for the exam, you should learn this phrase. Standing waves occur when 2 waves with the same frequency and amplitude traveling in opposite directions interfere with each other. Learn that sentence. They may occur when a wave interferes with its own reflection, which is what's happening here. The wave travels along the string, yes, and then when it gets to that end, it reflects. And so we have these 2 waves interfering with each other, and at certain frequencies we get this special kind of a wave, a stationary wave or a standing wave. These are the first 3 patterns that we see. The lowest frequency pattern is where we just see one single loop. You don't need to know that's called the fundamental. We are going to call it the first harmonic, and then 2 loops is the second harmonic, and then 3 loops is the third harmonic. The amplitude, notice that they're getting smaller and smaller, so you'd be lucky to get more than a 4th or 5th harmonic, really. I mean, have a play, that's why it's there. And these are the different harmonics, and they occur at higher and higher frequencies. In fact, if your first harmonic is happening at a frequency, let's call it F0, that's your fundamental frequency, then the second harmonic will be 2F0, and the third harmonic will be 3F0, etc. Okay, multiples of the fundamental, multiples of the first harmonic frequency. Remember that each loop is half a wavelength. Yes, so each loop is half a wavelength. So for the first harmonic, the length of the string is half a wavelength. For the second harmonic, the length of the string is a wavelength. because it's 2 halves. For the third harmonic, the length of the string is 3 half wavelengths, 3 lambda over 2. Each loop is half a wavelength. Each loop is half a wavelength. Nodes are where the string isn't moving, the amplitude is 0. Antinodes is where the amplitude is greatest. So on this second diagram here, that's a node, capital N. There's an antinode there, there's a node there, there's an antinode there, and there's a node. Not a nerd, a node, N-O-D-E. Okay. Standing waves will only occur at frequencies where the length of the string is equal to a multiple of half wavelengths. Now, what might you be asked to do? Now, looking at the second harmonic, I actually use the second harmonic when I do this with the class. I don't say do it for the first harmonic, I say do it for the second harmonic. Why? Because then the length of the string is a wavelength, and it makes the maths a little bit easier. Investigate one or more of the factors that affect the frequency at which the second harmonic occurs. So, at what frequency do you get the second harmonic? Yeah, and what does that frequency depend on? It depends on the length of the string, it depends on the tension in the string, and also it depends on the mass per unit length of the string, how heavy the string is. Yes. Now, you might be asked to do it for the length of the string, you might be asked to do it for the tension in the string, or both of those two. I doubt very much you'll be asked to do it for the mass per unit length of the string. Okay, you would need a range like, 6 or 7 different thicknesses of string to do that. It would be a little bit awkward, but the first two are relatively easy to do. So that's probably what you'll be asked to do, one or both of those two. So what should the relationship be between the second harmonic frequency and the length of the string? What should the relationship be? Well, now for the second harmonic, the length of the string is lambda. We have V equals F lambda, which is your wave equation from GCSE. So F equals V over lambda. Now V is the velocity of the wave, and the velocity of the wave in a string is root T over mu, where T is the tension and mu is the mass per unit length. In this experiment, both of them will be constant, therefore V will be constant. So if V is constant, then F is inversely proportional to L. Okay, so we should find that this frequency is inversely proportional to L. So F is proportional to 1 over L. So what we do is we do 6 or 7 different lengths between 50 and 100 centimeters. Depends on the length of your bench actually. For most physics lab benches you can manage a meter, but you struggle a bit to do more than that. But from 50 to 100 centimeters, repeat and average your results. Put your results in a nice table in Excel, and then F against 1 over L should get a straight line, and that confirms that relationship. Okay, what about the tension in the string? What should the relationship be between the second harmonic frequency and the tension in the string? Well, for the second harmonic, L is the wavelength, we have V equals F lambda, and we have V is root T over mu. So looking at that, we have this time the length is the same, so lambda is the same. So the velocity V is proportional to the frequency, therefore the frequency will be proportional to the square root of the tension. So what you do is you can increase the mass from 100 grams to 800 grams, measure the frequency, assume it as it's just the relationship that we're looking for. If we assume that each 100 grams has a weight of 1 Newton, that's not a problem. Okay. Repeat and average your results. One problem I find is that when you get to 800 grams, the vibration generator starts sliding across the table because it's being pulled by the string. So you might need to hold it down with something to stop it sliding. When you do the experiment, you'll know what I mean. Uncertainties. What uncertainties? Well, what are we measuring? We're measuring the frequency and we're measuring the length of the string. Now, if your signal generator's got a digital output, then you can assume that that is accurate and it will be precise enough. Okay, it'll be to the nearest hertz or to the nearest 0.1 of a hertz, whatever. If it doesn't have a digital output, then you could rely on the dial, which is like a scale thing with an analog kind of scale thing. Or better than that is get an app on your mobile phone. What you should do if you're an A-level physics student, on your mobile phone, get Physics Toolbox. Download it on your phone, and you can use your phone to measure magnetic field strength, acceleration, light intensity, frequency. It's an amazing thing, Physics Toolbox. And so you could use that to get the frequency. Okay, and that would be a very accurate way of doing it, very little uncertainty. Measuring the length of the string, there's a little bit of uncertainty where the position of the nodes are, because obviously on the vibration generator, that's bouncing up and down like crazy, so that's not really a node. The node is kind of pretty close to it. So there's an uncertainty of about a centimeter at either end in where the node actually is. So a little bit of uncertainty to consider there. Not enough for error bars, I would say. Okay, these are the bits that when your teacher marks it, they will make sure that you've done that, and that. Read it for yourself. I think it's pretty obvious, pretty straightforward. One little tip, when you're actually doing your experiment, take a photo of it and include a photo in your report. Okay, the physics moderator, last time he did me, he said that looked really good in the student's report.